Hi everybody, welcome back to Algebra 2. Today we are going to continue our study in probability with a section on conditional probability. Conditional probability is probability of something given that something else already happened. So you'll be saying, okay, well, maybe of all the people who made this choice, what percent had this quality? And so that's called conditional probability. So in other words, given that event A has already happened, what is the chance of event B? So we're talking about like two different events and like a subset of an event that's already happened. We read this out loud. This is probability B given A. This is a vertical line in between the B and the A. So just note that. There is a formula for it. Sometimes I'll use it, sometimes I won't. Generally, I try to avoid these formulas unless I absolutely have to have them, just because if you try to stick to formulas all the time with probability, it can come back and make things overly complicated. But here is the formula. The probability of B given A is the probability of A and B together divided by the probability of A. Now, I do like, though, that whenever you're working with this, see how that is on the bottom, that's on the bottom, like on the right, kind of looks like a fraction bar. It's not a fraction bar, but kind of looks like one. That is the denominator of the fraction. So I do like to make that connection. Okay, so in example 1, if you look in your workbook, example 1's on page 552 in volume 2. Now, let me pause this. Now, your workbook does not have this chart, but you should pause and copy this chart down or add it to your notes, so that way whenever you go back and look at your notes, it will make sense so that it doesn't look like you're just pulling numbers out of the air. So you do need this information. Go ahead and add it. Part A says, what is the probability that a member of the drama club is a sophomore? Now, this one I wouldn't necessarily use a formula for, but it is important that I understand the question. The question says that given that the student is a drama in the drama club, what's the probability that they're a sophomore? So that means I'm looking at just my drama club people. So given that they're in the drama club, well, in the drama, there is 17 kids. So that would be my denominator. Probability that they're a sophomore and in drama, 3. So 3 out of 17. That's pretty easy. Now, let me show you what it would look like with the formula. So setting the formula up, I would need to find the probability that I have a sophomore and drama student and divide that by the probability that the student is in drama. So let's see those numbers. Let's see, probability that a student is a sophomore and in drama would be, I need that pen, would be sophomore and drama, this student, 3 out of 115. So 3 out of 115 for the numerator. The probability that the student is in drama, well, there are 17 students in drama out of 115. And then 3 over 115 divided by 17 over 115 is 3 over 17. So I end up with the same thing, just took me an extra step. You can do either, but if you don't have to use the formula, you don't need to. All right, part B is saying, what is the probability that a sophomore is a member of the drama club? So it sounds like the same question, but look at the order. This time I'm finding what's the probability that a sophomore is a member of the drama club. So out of all the sophomores, what's the probability that sophomore is, that you have a sophomore that's in drama club? So I'm finding the probability of a student being in drama club given that they're sophomore. So that means this time I'm only concerned about the sophomores. So in total, there are 36 sophomores and 3 sophomores in drama club. So 3 out of 36 does reduce to 1/12. Now we have this idea of conditional probability and independent events. Now remember, conditional probability is finding the probability of one event happening given that something else already happened. So I like to think of conditional probability as the probability within a subset. So like subset. Like in the previous example, we had sophomores. Sophomores, juniors, and seniors. So our sophomores were a subset. We were calculating probability just for that subset of sophomores. Independence is when you are trying to see if one event outcome has an effect on the other one. So in the example before, would the fact that you knew someone was a drama student, would that help you know if they were better know if they were sophomore, junior, or senior? Does being in drama have anything to do with the grade level? Does being in the art club have anything to do with your grade level, or vice versa? So there is a test for independence. Now we have, like you might think, oh no, it really doesn't. Like thinking of your own experiences and what you have noticed, but we will be measuring independence based on the data that we have. So like for our numbers that are in our example. So you might have like one set of data that says these two events are independent, and then you might have another set of data that says they're not independent. So we only measure independence for a specific set of data, not in general. And we don't make generalizations, we just look for a specific set of data. So to test that, we have a formula or a way to test if two events are independent. So if the conditional probability is the same as the probability of B by itself, then, and also is the conditional probability of A, given that B happened, if that's the same as the probability of A happening by itself, if those are the same, then those two events are independent. If they're not independent, we call them dependent events. So we will look at an example involving that, example 2. Again, on example 2, you're going to need to pause the video and I'm going to zoom in. Pause the video and copy down this chart because it's not in your workbook. So pause, copy it down. So the table below shows vehicles in a parking lot garage one afternoon. A vehicle is in the garage will be selected at random. Let B represent the fact that the vehicle is black. Let V represent the vehicle is a van. Are the events B and V independent or dependent? So let's figure that out. Let's find, first of all, the probability. We want to know B. I'm just going to write it down. B is black vehicle, and V is going to represent van. Now, I don't think this example in yours? C and car? No, this is an extra example. Okay. So let's look at this. Probability that a vehicle is black. Let's see. In general, how many black vehicles are there? There are 13 black vehicles out of 22. Now, if I want to know if this is independent of the type of vehicle, then it would be independent if this probability is the exact same as the probability of having a black vehicle, given that I know that it's a van. So let's figure that out. Erase what I've got. Now let's go back to the formula for conditional probability. This would be me finding the probability that it is black and a van divided by the probability that it's a van. All right, so black and a van. Okay, so black, van, there's 3 of those. out of 22 vehicles total. And then probability of having a van, oh, there are 3, 22. So 3 over 22 divided by 3 over 22 is 1. So the probability of seeing a black vehicle, given that you know that it's a van, is 1. So pretty much, because this is 1, it's certain to happen because there are no red or white vans. So this tells me that if you are like, okay, I'm going to pick a vehicle in the parking lot, and you say, is it a van? And then I say yes, then automatically you know it's going to be black because that probability is 1. Now that's not the same as the probability of choosing a black vehicle. So these events, because these numbers are different, this number and this number, because they're different, these events are dependent. Knowing the probability of one thing can give you clues about the probability of the other thing. So these events are dependent. I wrote dependent. Now this one is in your workbook, so let R represent the probability that you're selecting a red vehicle, and C represents the fact that you're selecting a car. Are those independent? So let's see, let's find the probability of a red vehicle. Let's see, so there are 11 red out of 22, which is 1/2. Okay, so then let me find the probability that I get a red vehicle, given that I know that it's a car. So that would mean I need to know the probability of a red and a car. Divide that by the probability of getting a car. Okay, probability of red and car. Red car would be 5 out of the 22 total. I need a fraction here. So 5 out of 22 over the probability that I have a car. There are 11 out of 22. Oh, I calculated that first probability wrong. Hold on a second. So 5 over 22 out of 11 over 22 is 5 out of 11. Now, for red, I miscalculated this, so let's go back. Let's try that again. I think it gave you the probability of a car. Okay, probability that this is red. How many reds are there? 7 out of 22. There we go. Now, if I want to see if these two events are independent, is the probability of a red, 7 over 22, the same as the probability of knowing I have a red vehicle given that I know it's a car, 5 out of 11. Now, those may be close, but they're not the same. So no, these are dependent. Dependent. You also have some information missing on example 3. You need some information given to you about a concert survey that was given. So all this information right here. And then this is like a pre-example leading up to the example in your workbook. So we will do the example 3 from your workbook, but we're going to do this one first. But you do need to write down the survey results. So there was a survey that was done. It asked students 2 questions. Basically, it asked them if they planned on attending a concert, and then it asked if they were fans of the band who was playing. So since they're giving me, first of all, it looks like they've asked the students 2 questions. First of all, are you going to plan to attend? So 70% plan to attend, 30% do not plan to attend. Then it says it asks them another question if they're fans. Now, I don't know what percent overall were fans and what percent were not, but I do know that 80% of the students who plan to attend are fans. So because they've asked everybody 2 questions and they're giving me this divided up percentage, this makes me think I should make a tree diagram. So it looks like the first question they asked is, are you going to attend or not? So first question, attend or not. So I'll say attend or not. Okay, and whenever you're making a tree diagram, you want the 2 branches to add to be 1 because we want to account for all the percentages. So, whoops, let me erase that part. Here we go. So I know that 70 students plan to attend, so 0.7 here, or 0.70. And then I also know for sure 30% do not plan to attend, so I can put a 0.3 here. And then if I notice 0.70 plus 0.30 is 1, that's what I want to happen. All right, then I know that of those who attended, 80% of those are fans. So I'll have fans here, and these guys are not fans. And then the same question was asked for those who did not attend the concert, fans and not. Okay, of those who attended, 80% were fans of the band, so 0.8. And that means I can assume that of those who attended, 20% were not fans. Maybe they're just going to hang out with their friends. Then of those who did not attend, 25% were fans of the band, while 70, I can assume 75% were not, because for this branch to add to 1, then that has to be 75%. So here I have my tree diagram of all the probabilities. Now I can begin to start answering the question here. So the question they're asking, again, this is an extra example. What's the probability that a student surveyed plans to attend the band's concert and is a fan of the group? So here I can just follow the tree diagram. Plans to attend and is a fan right there. So I just do that and is a fan. So that means they're asking me the probability that they attend. I'm going to abbreviate attend ATT, and they're a fan, is, I multiply these two together, 0.7 times 0.8, which is 0.56. Cool. All right, so now let's look at that part B that you guys actually have. My tree diagram's going to travel with me. Okay, what is the probability that a surveyed student plans to attend but is not a fan of the group? So here, plans to attend but is not a fan of the group. So I could say probability that they attend and they're not a fan. This is not fan. Then I would multiply 0.7 times 0.2. That would be 0.14. Now, where does conditional probability play into this? Well, this diagram tells me about the attendees who are fans or not, and then the people who didn't attend, if they're fans or not. But if I wanted to know, let's say, the probability of all the fans that they attended, then that's a whole different question. So let me write that down in a different color. What's the probability that, what's the probability that, given that they're a fan, so out of all of their fans, what's the probability that they attended the concert? So it is a different question here, which means I'm going to need to set up the formula. So I'll need the probability that they attend and they're a fan. I want to know the probability that they attend and they're a fan and divide that, that's an F, by the probability that they're a fan. Now we did find the probability that they attend and they're a fan earlier because that was this part, attend and a fan. We found that to be 0.7 times 0.8, which is 0.56. So equals my numerator, it's going to be 0.56. But for the denominator, what's the probability that they are a fan? Well, let's see, fans attended and they also did not attend. So I also need to include those who did not attend, but also were fans. So I need to include this branch as well, which is 0.3 times 0.25. And that is 0.075. So 0.075. And this was 0.56. So the probability that they're a fan, I just add those two together. So the denominator is going to be 0.56 plus 0.075. So then when I do all of this, 0.56 divided by 0.56 over 0.075, I get 0.88. Which is the answer to this extra question here. So of all the fans the band has, 88% of them attended.